Lab experiment 2 consisted of demonstrating Newton's second law, net force equals mass times acceleration, by testing the motion of a falling object. The purpose of this experiment was to determine and model the effect that air drag has on an object in vertical motion. This was performed by dropping an empty can from a height and tracking its motion with a software tracker. Hypothetical models were also constructed and close-stripped to demonstrate the object's motion with various forces. One model included only the force of gravity on the object, while the other also included air drag. Position versus time data was collected from each of these models and compounded in a singular comparative graph. The main overall result of the lab was that without air drag, the can would have traveled with a higher velocity due to a lack of opposing drag force, which lowered the net force in the negative y direction. The lab also showed some discrepancy between modeled motion with air drag and experimental motion. However, they were very close in the end, much closer than the model without air drag. In the real-world experiment, an empty can was dropped from a height and recorded until it hit the ground. For the coordinate axis in this experiment, the origin was designated at the center of the can in the first frame, with the x-axis spanning positive to the right and negative to the left. The y-axis was designated positive upwards and negative downwards. The initial conditions were a position of 0.005 meters positive in the vertical direction and an initial velocity of negative 0.578 meters per second in the y direction. The distance and tracker was calibrated from the known length of the can. The frame rate of the video was 1 frame every 1/30th of a second. These conditions were input in the computational models as well, ensuring that the models accurately calculated data. Here's the real-world experiment being performed. Note the moving center of mass used to calculate the can's position in each frame. Here's the model utilizing only the force of gravity. Here are the graphs. Note the steep slope of the position versus time graph that matches with the large velocity. Here's the sole force, gravity, acting on the model represented by a single arrow pointing downwards from the origin of the object. Here's the model utilizing both gravity and drag force. Here are the graphs. Note how the slope is less steep than that of the gravity-only graph and how the final velocity has a smaller magnitude. Here are the forces acting on the can, gravity and drag, represented by arrows. The force of gravity stays the same, but the drag force increases until it evens out with gravity and the net force is 0. All of the initial conditions were put into these codes, as well as delta t being designated as 1/30th of a second in order to match the progression of the frame rate of the video. All of these were implemented in both codes, and they were consistent in both cases. Here's the gravity-only code. Note the net force, which is made up of force of gravity, mass times acceleration due to gravity. 9.81 times the mass of 0.012 kilograms yielded that force here. Next, the ball velocity was calculated. Using the known acceleration, 9.81 meters per second squared, I found the change in velocity to be negative 0.32373 meters per second per 30th of a second, in time with the frames. The ball's position was calculated using the position update formula, starting with the initial position and then adding the average velocity multiplied by the time passed. In the model with air drag, it is necessary to find a proportionality constant. A constant of 1.311 was determined from comparing the ideal model to the experimental data. Here, speed was designated to be the magnitude of the ball's velocity. This was so that it could be squared in order to be used to calculate the drag force, seen here, and added to the gravity force in order to find the new net force. The velocity in this model was determined from the velocity update formula seen here, and the position updated as well with a new average velocity. As mentioned previously, terminal velocity occurs when the magnitude of the air drag force equals that of the gravity force, rendering the net force 0. When this happens, the velocity that the object is at will remain constant from there on out or until acted upon by another force, resulting in a non-zero net force. Looking at the velocity graphs of both models, with and without gravity, only one seems to predict a terminal velocity. The reason that the one with only gravity does not predict a terminal velocity is because that no other force acting upon the can turn the net force to 0. In the other graph, there is a force, however, the air drag. At the bottom right of the graph, you can see the velocity tapering off to become more constant with a slope close to 0. That is because the air drag is acting against the force of gravity, and that is why this graph can predict a terminal velocity. In the case of throwing an object, the object's terminal velocity would remain the same. Due to the fact that the force of gravity on an object never changes as long as it's relatively close to Earth, the amount of drag force needed to bring the net force back to 0 does not change either. If an object was thrown, it would reach terminal velocity faster due to an initial higher velocity, but the terminal velocity itself would not change. And to go further, if something was thrown faster than its terminal velocity, air drag would work to slow it down back to its terminal velocity, as demonstrated in this approximate graph. Conclusion, looking at the comparative position versus time graph, it can be seen that there is a significant difference between the experimental data and the gravity-only model data. This, as previously discussed, would be due to air drag decreasing the magnitude of the net force, which in turn would decrease the object's acceleration and velocity as stated in Newton's second law. There is also a slight difference between the model including air drag and the experimental data. While the data is much closer, there must have been errors that led to the differences. Because both the model and the real-world experiment only contain drag force and gravity, the error was most likely due to inaccurate calculations of the proportionality constant, or issues with trackers such as misaligning the center of mass, measured distance, or any issues with rounding or coding in GlowScript.